Okay, so we're going to continue with 4.6 today, Fundamental Theorem of Algebra. Number 1 and 2, how many solutions does the equation have? How many solutions? It has 4. Okay. How many zeros? It has 3. Okay, now zeros can be real zeros or they could be imaginary. Now, the confusion came earlier when we were talking about it. They're like, well, it doesn't mean it crosses the x-axis 3 times. That's right, but that's called an x-intercept. I know we use the term solutions, x-intercepts, and zeros interchangeable, but a zero could be a real zero or an imaginary zero. If it's a real zero, then it's an x-intercept. If it's imaginary, it's not an x-intercept. We clear on that? Okay, so listen to the terms we used there. Questions? Hallie? Yep. Now, if you find the zeros, when you find the zeros, though, like if we were actually solving, you would set this equal to 0. Yep. All right. Find all zeros of the polynomial function. Now, this means we actually have to, it's not asking how many, though number 3, we actually know how many there are. How many are there? There are 3 zeros. Okay, I want you to find those 3 zeros. Make sure that we're all kind of on the same page. Can we do any greatest common factor out of here? Factor by grouping? No. No factor by grouping either. Yeah, bummer. How about possible zeros? What are the possible zeros? Okay, I need everyone's attention back up here. Possible solutions are factors of 12. 1, 2, 3, 4. Okay, so all those factors divided by the factors of our leading coefficient, which in this case is 1. So we get 1, 2, 3, 4, 6, and 12, all divided by 1, which right now that's quite redundant, but we'll put it there just because we're still learning it. This plus minus. Okay, and then we test. Now, 1 is not going to work just because these are all positives. Everything's positive. 1 definitely does not work. You add the coefficients, you don't get 0. Does negative 1 work, though? No. Okay, and just because we're going to actually apply this a little later in class or something like it, when I put negative 1 in, really, which of the powers change? Like when I put negative 1 for an odd, does that change my coefficient? What's a negative times negative times negative? Negative 1 times 1 is? Negative 1. What's a negative times negative? Positive times 7 is? 7. So did the coefficient change? No. Okay, this, would the coefficient change? Yeah. And that's 12. But does that add up to 0? No, so this one does not work either. So 1s do not work. Now, would I test positives or negatives probably? Negatives, because I got a bunch of positive. Everything's positive. If I test the positive, I'm just going to get a lot of positive. Okay? Which is good if you're trying to be happy, but not so much if you're trying to do this problem, which some would argue that means you're not happy. But it's kind of sad, actually. All right, negative 2. Negative 2. So we'll put that in. We'll go 1, 7, 16, and 12 so that we're not confused. Let me kind of wipe that out there. Okay, this becomes 1, negative 2, 5, negative 10, 6, and negative 12, 0 with sprinkles on top. All right, so we have this factor, x, what is it? Plus 2. And this right here, all right, 5x and 6. Okay, all that equals 0. Okay, we plugged in 0 here. We didn't actually show up, but there we did. Okay, this x plus 2, we obviously know the answer here, but does this factor? X plus. All right. So, my zeros Here I get negative. So x equals that. Now yesterday the question came up, do I have to list the negative 2 twice? I would probably accept it with that, with just negative 2 and negative 3. But if it's when it says, I would accept it. When it says all zeros, I could see where a teacher would argue, look, I want to see negative 2 appear this many times. Okay, so it doesn't hurt you to write the extra negative 2 unless it's like you have to write 100 times negative 2. Okay, then you might like start hating negative 2. Okay, but when it's just twice, probably a good idea at least just to write them out. If it says list all multiple zeros in the solution, then you must list the negative 2 twice. So if you're like, I can't remember, then just always list it. Always list the multiple zeros, and you'll be fine. Yeah. Yep. Yeah, so if there was an x squared out here, that would mean there was 0, 0 out there. Yep. Okay. But there's not. So. All right. Number 4. There we go.
That's Allison and Colt's work of...
Hey guys, no greatest common factor, but Chase asked a good question. Could you do like 3 groups to do factor by grouping? You could try it. It's not going to work. Okay. So I just default right into my possible solutions here. I know a lot, right? 1, 2, 4. But then you have to divide by your leading coefficient. Huh. Labor intensive. This doesn't look like that bad of a problem. Does 1 work? Man, that's even better. 1 works. Jeez, negative 1 works, and this is an easy problem.
I messed my signs up somewhere.
Okay, so we get x minus 1 and x to the 4th minus 2x plus 2x cubed plus 3x squared plus 2x minus 4. All right. All equals 0. Our hero. Yeah. Now we have an x to the 4th. We still haven't made it to the coveted x squared. No factor by grouping. No greatest common factor. So, possible solutions. Keep going. Hey, the joy just continues, man. This is like the gift that just keeps on giving. You ever seen the movie Groundhog's Day? Yeah. Here we go. Yes. Good idea. Think about it. I think I get negative 1 to work on this one.
Well, McCoy, you got to give us a little bit of time.
I thought I heard someone earlier say negative 1 worked. Did negative 1 work up here? Yeah, that means for all you that used 1 up here, negative 1 will work down here then. And if you're like, man, I used negative 1 up here, and we used 1, then 1's going to work down here. Got to get that factor somewhere. Woo! Another donut. Don't mind if I do. So we bring down our x minus 1. Here's our x plus 1. And then we have to go x cubed minus 3x squared plus 6x minus 4. Hey, can we do factor by grouping?
Nope.
Man, we cannot. So possible solutions.
Go.
Same thing.
This is fun.
This is really fun.
Do 2, you do negative 2?
All right, I'll let you guys get ahead of me.
Okay. 2. So you're doing negative. Because we already did one. When was the first one?
Be nice to get that to actually focus. Let's try to
Fine, I'll do negative 1.
focus better. There we go. A little better.
So mean to me.
Oh, no. Oh. Hey, we're not into the dividing and conquering here. Just dividing. Okay? 1 works, I think. Now, if your table partner there said it didn't, don't get mad.
Andrew, I'm mad.
Woohoo! Dude, so we get another x minus 1. Another x minus 1. Hey, and now we got down to the coveted quadratic. Yay! Cool. Can we factor now?
Yeah.
Yes.
Does that factor? No, we got to use completing square quadratic formula. Opposite. That should be easy. Like quadratic formula, after doing all that, you're like, oh, dude, that's easy. It just... Well, at least we didn't make it all that complex for you. Okay?
Yeah, it's imaginary.
It's imaginary.
Oh, we did make it complex.
Yeah, McCoy. You did.
Imagine that. Hey, it says find all zeros. Does that include imaginary?
Yeah.
Yes. Gotta keep going. Come on, you can do it. 2 plus minus root 4 by root negative 1 by root 3. That makes root negative 12. So this is 2. This is I. This is root 3. Yeah, so we call it 2 plus minus 2i root 3. All over 2. Are we done simplifying?
No, you gotta add it.
2 and 2. This cancels. 1 plus minus I root 3. Now, is that the answer? No, that's just this part of it. 1 plus minus I root 3. We have all these other pieces. 1, negative 1, and 1. How many possible solutions should we be able to have? We should have 5 solutions, right? And we have 1, 2, 3, 4, 5. We found all 5. We're amazing. Okay? Any questions? Can you just take out yesterday's assignment, please? So any questions, especially on these bottom ones here from yesterday? Okay. 7 and 8. Everyone get first, well, let's just really quick with number 5. We'll write a polynomial function of least degree. Okay, so in other words, we're not going to have repeated zeros. The rational coefficients. Okay, we're not going to have imaginary coefficients. Now, we obviously have some imaginary solutions. And a leading coefficient of 1. Okay, so if these are given 0, so just, I'm assuming everyone found this one not too bad here. If that's negative 4, we have x plus 4. If this is 1, we have x minus 1. Because when I set that equal to 0, I get 1 as a solution. And This is x minus 7. And then we multiply it out, and we get our solution of x cubed minus 4x squared minus 25x plus 28. Okay, obviously I'm assuming you can multiply it out. All right? Well, when you go to this is something we've already covered. We went through a theorem that said, hey, if you have a negative root 5 as a solution, you also have a positive root 5 as a solution. Okay, so that means this is going to be a third degree because there are 3 different zeros. This is f of x equals, okay, we have the x minus 10, but then we have to figure out what we're multiplying that by, and that quadratic gives us these 2 pieces. So the book goes through it one way. The way I talked about doing it is just setting this part equal to x. I know x equals negative root 5. And so if you crank through that and solved it, and actually let me give myself some room, bring it over here. Okay, I'd bring the negative over, I get negative x, and then I would square both sides to get rid of that root, so 5 equals x squared. And then I would subtract the 5 over, so I get x squared minus 5 equals 0. This is the quantity that goes right here. And please note, if you actually were to solve this out, right, the reason this works to give you both these solutions, because if I actually went through now and found the solution to that function, the first thing I do is I'd add 5. I get x squared equals 5. And then I'd take the square root, and when I put that square root in, it gives me plus minus root 5, which are both of those solutions. Okay? So then we'd multiply it out from there, and I assume you can do that. That gives you that x squared. X cubed, excuse me, minus 10x squared minus 5x plus 50. Okay? Yeah, Hallie. Just divide by negative 1. This is a negative 1 out here. So to go from this step here to that here, you just divide each side by negative 1. So negative 1, or 1x divided by negative 1, it gives you negative x. Okay? Okay. Yeah. So to go from here to here, I square this side. Yeah. Negative times negative is positive. Okay? That's all right. Any other questions there? The reason I go through that is because now we're down here. And one of the theorems we did not go through yesterday talks about complex conjugates. Okay? And we have 8 and 3 minus I. If you have one imaginary in terms of A plus BI, you're going to also have the other imaginary, just like we have with our radicals. Okay? Does everyone, to make sure we're clear, does everyone understand how this ended up giving us 2 solutions? Okay? The same thing happens here. So if I set this as f of x, let's show why that works. And I say x minus 8, that gives us this piece. But then this part right here, I am going to say 3 minus I equals x. We know that's a solution. If that's a solution, then the way I get that solution, I'm going to kind of work backwards away from the solution so I get the equation that came from. So the first thing I do, I'm going to go ahead and move that 3 over. I have negative I equals x minus 3. We good so far? Yep, because there's a negative in front of it. Oh, negative I. I forgot the negative. There we go. Okay? And then from there, what is I? Root negative 1. So this I is actually root negative 1. So I have negative root negative 1 equals x minus 3. Does everyone see where the other answer is going to come from? So the next piece is to divide by -1. This becomes -x and +3. We flip both those signs. And then how do I get rid of that? I square it. So I get -1 is equal to -x plus 3 quantity squared. All right? So this piece right here becomes x squared minus 6x plus 9. If we multiply it out, we have, and then we have the -1 here, so we're going to move that back over to now get x squared minus 6x plus 10 equals 0. That is the quadratic that goes right here. That's why you get two solutions. You get your both of those. Okay? So if you know you have one, you automatically have the other. All right, this is why. Actually, it's x, but you know. Okay? Just have to use your imagination. All right. So from there, you multiply it out, correct? Okay, and I'm assuming you can do that, but you get x cubed minus 14x squared plus 58x minus 80. Okay, pretty sure that you guys can multiply it out. Okay, and then we just, for fun, make it so you have to deal with an imaginary and an irrational in the same problem. So this what degree is this going to be? You have 1 degree there. With that you have 2 minus root 2, but you also have 2 plus root 2. And this you have 2 plus 3i and 2 minus 3i. So it's a 5th degree. Okay? All right, you guys understand a little better? All right, I'll put that answer, that's the work for number 8. I'll hang it up if you want to check it. It's also going to be online so you can kind of see it, but going through the same process. You're not going to have time to copy it all down right now. All right, because I'm about to move past it. It's amazing, I know. All right, so this is example 4 out of the book, and it's talking about determining how many positive real zeros, negative real zeros, and imaginary zeros. Okay, so there's 3 different things we're looking at. Positive, negative, and then our imaginary. Okay, well there could be. There might not be. What we know right now is that there are a total of how many zeros? 6. There's 6 zeros, so there's a total of 6 zeros. Now I'll let you copy this down. I'm going to give you time to copy that down, and I'm going to actually make a table down here to help us out. Positive real, negative real, and imaginary. What's that? No. Sorry. Skipped yesterday in the lesson was we didn't talk about Descartes' rule of signs. We also didn't talk about the complex conjugates theorem that we just covered. All right? But now we've talked about that. All right? And conjugate sounds cool. So does Descartes. Okay, the math dude. All right? Yes. Okay, so this, just so you guys are clear, this notation, you're going to see it a lot. All that means is I have what do I have? That's a polynomial. It's a polynomial with a sub n being my leading coefficient, and I have a degree there, and a sub 0 being a constant. The rule of Descartes says the number of positive real zeros of f is equal to the number of changes in the signs of the coefficients of f of x, or is less than that by an even number. That's for positive real zeros, and it does the same thing. The number of negative real zeros of f is equal to the number of change signs of the coefficients of f of negative x, or is less than that by an even number. So what does all that mean? Well, that's what it says word-wise. Let's actually see what it means. What it means is if I look at a function, f of x, and I look at the coefficients, this has a coefficient of 1, and I say, hey, look, it's positive 1, and this is negative. That means my sign of my coefficient has changed. It's went from a positive to a negative. Therefore, we're counting that as 1. Then it goes from negative to positive. Now we're up to 2 sign changes. Now we're up to 3 sign changes. Did it change? Did it change? Did it change? No. Okay, so we have 3 sign changes. That means the number of positive real zeros I can have is 3. Good? Just counting sign changes. Yeah. If it was plus 8x, yes, then I'd have to, if that was a plus right there, I'd have to go with another sign change. Yes. We can go into why it works later. I'm not going to be able to have time for that right now. But I can teach you the rule right now. Okay? I could try to find some info to put on the website too if you want to research it a bit more. No, I don't want to do that. But I definitely know I won't have time today to go into it. So this being, if I want to find how many negative real solutions, first, how many solutions total are there again? 6. So right now I know I have 3 more solutions somewhere. They're either negative real or they're imaginary. And so what I have is f of negative x is going to help me with my negative real. Now let's go back here real quick. We just did this. As wordy as that sounds, we just did this first bullet. We're doing the second bullet now with f of negative x. And f of negative x, you don't switch all the signs. Some of them change, though. When I put negative x in for x to the 6th, does it change my coefficient? No, because negative times negative times negative times negative times negative times negative is still positive. So this, when I put that in, I still get 1x to the 6th. Right? When I put negative x in for here, well, when I raise a negative to an odd power, my result is it's negative times negative is positive, times another negative is negative, times another negative is, and then so times the 5th negative is negative. That means I get a negative x to the 5th here times negative 2. Negative x to the 5th and negative 2 is, that is positive 2x to the 5th. So it changed the sign. So what does it appear the rule is? Might be a little early to figure out a rule. Let's put it in here. Negative x to the 4th. Is the sign going to change? No, because it's even. So this becomes plus 3x to the 4th. Stays 3x to the 4th, excuse me. Is it going to change here? Yeah, we get minus 10 negative x to the 3rd. That negative gives me a negative x times negative 10 is positive 10x to the 3rd. Will it change here? No. Because it's an even. Will it change here? Yes, because it's odd. And then this is just constant. It stays the same. Okay, so now to find the negative real solutions, look for sign changes. Does it change? Does it change? Does it change? Does it change? There's 1. Does it change? There's 2. Does it change? There's 3. So if there are 3 positive reals, There's also 3 negative reals, which means how many imaginary? 0. Now, that wouldn't be so bad. Here's where the last class got a bit confused. And once again, I blame teaching. But before we go into that, any questions there? Okay. Now, there's one part of the rule we haven't really spent much time looking at, and that's this. Or is less by an even number. So it's equal to the number of sign changes, or it is less than that by an even number. So if I take an even number away from 3, what do I get? I get 1. So if that's 1, and this still could be 3, what's that make this? This is 6, 2. Okay? So it could be 1 or 3. I could have 1 or 3 positive real solutions. The same thing applies here, though. I have 3 negative real solutions, but I could also have 1 negative real solution. So I have to list all my possible combos. I could have 3 positive real and 1 negative real, which means I have how many imaginary? 2. Go ahead and list your last. There's one more option there. Okay, what's our other option? Good. We could have 1. We could have 1 and 4, which means we have our 6. Okay, so what I found that might help you out a bit. So if I was to redo this table, knowing what I know now, so if I was to build this table again, like if I was to do this problem over, when I list my positive real, my negative real, my imaginary, and my total, it might be helpful when you start it, you go, hey, there are 3 positive reals. Well, that means there also could be, that means maybe skip a line or 2, there could be 1 positive real as well. Right? It's either 3 or 1. And when I get here and I go, well, I just found that there's 3 negative reals. Well, there also could be 1 negative real. Okay? So now, if I have 3 positives and 3 negatives, well, I could have 1 positive and 1 negative, and I can have 3 positives and 1 negative, and 1 positive and 3 negatives. So you could rebuild the table in a different way if you want, if it helps seeing it like that. Okay, this would be 0, this would be 2, this would be 4, and that would be 2. Same table, just kind of looking at it in a different way. Okay. Let's see if you can maybe do it there. Give it a shot. Number 9 and number 10 there. Actually, let's start with just one of them. Let's start with number 9. All right, so if I'm going positive, negative, imaginary, and total, this one, what are my totals? I have 3. Okay, it's a cubic. Any sign changes? Nothing there. Nope. We do get 1 here, though. So we get 1. All right. How about for our f of negative x? This becomes negative because it's an odd. This becomes negative, and it stays negative. Does it change? We get 0. Okay, which means how many imaginary? 2. Any other options? No, that's it, right? Okay? Good? All right, I want you to take a look at your assignment. Okay? Go ahead and turn your paper over to the back. Look at problem number, let's start out with number 17. Kind of the most complex one on there. Okay, this is asking the same thing. All right? Take a look at that one. Start building up your table there. So we have 5. So how many real positives? 3. Which means we also have an option of 1, right? You always have to do decrease by an even. How many negative? Yeah, it's 2, right? So switch signs here and then there. Now, when you have 2, if I decrease by an even, what's that give me? 0. So you also have to have 0. Okay? So I have 3, 2, and what makes 5? Well, that's 0. That's one set. Well, then I could have 3 and no negative reals. And how many imaginary? 2. Then I could have 1, 2, and 2. What's my other option? 1, 0, and 4. Any other options there? Oops, didn't realize that wasn't on there. We have our total of 5. It's kind of our set there. If you're looking at this, you could have a potential of 5 real solutions if you had. You just make up you can make up any polynomial you want. So this polynomial right here, if you multiplied it out, got x to the 5th, you would have 5 real solutions. 1, 2, 3, 4, and 5. They're all positive real. Go ahead. Sorry. Well, this one, because we only had 3 sign changes. So we only have 3 positive real. In this case, we can never have more because we only have 3 signs.